This meeting is being recorded.
So Amjad, you can begin.
Just a second. Can you see my slides?
Yes.
So maybe let me just how can I turn on my video?
Perfect. See you and your screen very well.
Yeah, so I will be talking about ghost condensate dark energy with a 6-order dispersion relation, and this is a work in collaboration with Ehsan Yousefi and Mohammad Jahani. Ehsan is a postdoc now at IPM, and Mohammad is a postdoc now at the University of Camerino, Italy. So the discovery of the current acceleration of the universe took the cosmologists by surprise. The simplest explanation was a cosmological constant with the value of 10 to power of minus 122 m Planck to power of 4, which is quite small and needs a fine-tuning of order 122 orders of magnitude in order to be explained, even using just anthropic principle. The upper bound that you would obtain is 2 orders of magnitude larger than this value, than the observed value, and explaining this small value would need fine-tuning. Another approach is modifying, another approach to explaining the acceleration of the universe is modifying gravity. And among modified gravity theories are scalar tensor theories, which would lead to long-range force, long-range force that changes by a constant factor. Another approach to modifying gravity is the Diwali-Gabbadat-Separati brain world model and the Fierce-Pauli theory of massive gravity. In both of these two theories, a scalar field, which we denote by pi, it interacts with matter with gravitational strength, and this is the thing that makes these theories healthy. In DGP brain world model, this is the brain bending mode, and in the Fierce-Pauli massive gravity, this is a longitudinal component of the metric. And in both these theories, they reduce to a scalar tensor theories on scales smaller than a IR length. Instead of GR, they reduce to a scalar tensor theory, but they become strongly coupled at lambda UV. The approach that I will be talking about and is known as ghost condensate theory. It is a modification of gravity with no strong coupling in UV, and it behaves almost like a cosmological constant in which we have a spontaneously Lorentz breaking background that breaks time translation too. And in this approach, the field velocity obtains a vacuum expectation value. Unlike massive gravitons, one has only one additional scalar field, which is a longitudinal mode of the metric, and it appears with a modified dispersion relation. So the term for the Gauss field appears with a sign opposite to the standard model field. But like what happens in Higgs mechanism, higher order terms like di phi to power of 4 stabilizes the theory. It was argued in the original paper by Arkani Hamed et al. That going beyond omega squared proportional to k to power of 4 leads to strong coupling at IR. For example, if one assumes that energy goes to SE and the dispersion relation is proportional to the sixth order to the momentum power of 6, then the scaling of time, position, and pi fields would be as follows. So t goes to s to power of -1, tx goes to s to power of -1/3 x, and pi is going to s, pi is going to pi, basically. And then the interacting operators like pi dot nabla pi squared would scale like s to power of -1/3. And basically, if s goes to 0, which would be like IR limit, then these operators, these interacting operators, would become relevant. In cosmological setups, however, approaching the IR limit is a bit tricky. For example, if during inflation, if there is a transition from k to power of 6 to k to power of 4 and k squared, before the theory becomes strongly coupled at lambda IR 6, one would have a consistent effective field theory, and this is what we examined in these two papers. In the case of late time acceleration of the universe, we know that this is a recent phenomenon that happened at cosmological time scales, which is about z of 0.7. So basically, modes do not really approach the IR limits in such setups. And maybe even effective field theories with pure six-order dispersion relation can make sense. The outline of my talk is as follows. I will talk about the structure of Gauss condensate with the six-order dispersion relation. Then I will talk about how strong coupling could be avoided within such setups in a late time cosmological acceleration. Then I will talk about the possibility of interaction of the Gauss condensate with six-order dispersion relation with the standard model fields. I will talk about Gauss condensate coupled to gravity in Minkowski space, and also coupling of Gauss condensate to gravity in de Sitter space. Let me just elaborate on the structure of the Gauss condensate with the six-order dispersion relation. Suppose you have an action S0 plus delta S, where S0 is given by this expression, where P of X is just an arbitrary function of di mu phi squared. Delta S contains operators which are quadratic order squared and cubic order cubic derivative of phi square terms. So if you vary the action, you would obtain this equation, di mu of the brackets equal to 0. And when gravity is ignored, you have a solution phi equals to ct, where c is an arbitrary dimensionless constant. If we look at the perturbations around such a background, the time and spatial kinetic sign of pi appear with the standard sign. If these two conditions, p prime of c squared is bigger than 0, and the other expression, p prime plus 2c squared, p double prime bigger than 0. In an expanding background, p prime is proportional. One can show that p prime is proportional to a to power of -3, and therefore the coefficient of di pi squared vanishes for the vacuum expectation value phi dot squared equals to c squared, c star squared. And then the dispersion relation would be purely quartic order. Now we are interested in obtaining 6th order dispersion relation. So we have to include the S3, S4 terms in the Lagrangian. So if you do that, the Lagrangian takes the form in the first line where m tilde squared is given by such an expression, and S bar term is given by a combination of S3 and S4. And in general, the dispersion relation would be a combination of quartic and 6th order terms. In order to have pure 6th order term, one either has to assume that this combination of S1 and S2 is equal to 0, or K is being much larger than m bar squared over S bar. And K is the longest mode that have exit the horizon, which is during the acceleration domination phase, which is h over 1 plus zc. So contemporary acceleration is like a low scale inflation, and like inflation, in order to avoid the strong coupling, one has to assume that one has to just guarantee that FNL is much less than the amplitude of perturbations to power of -1. So zeta in our language is given by -h pi, and FNL is the biospectrum, which is the expectation value of just the cubic zeta over the power spectrum squared, where power spectrum squared is just the 2-point function of zetas. For canonical fields, pi, c, and u, so the equation which is satisfied is the expression at the bottom of the slide. And in a de Sitter space where A is given by -1 over h eta, where eta is the conformal time, the solution could be obtained exactly. The 2-point function would be obtained by to be given by this expression in red, which is proportional to h over m squared. And you can also calculate the 3-point function of the curvature perturbations, noting the fact that interacting Hamiltonian is minus the interacting Lagrangian and is proportional to pi dot nabla pi squared. So if you calculate this integral, and if you focus on momentum, which has gone outside the horizon, and in the limit that h over m is much less than 1, you can see that FNL is less than zeta inverse if C star s to power of s bar to power of 1/4 is much bigger than 10 to the power of minus 34. And you see that C star and S bar would be basically, could be of order 1, and this condition would be easily satisfied. So actually, you can verify that the strong coupling becomes important, or mathematically FNL becomes of order zeta inverse if zeta star is about 10 to the power of 33, or roughly 77 e-folds from now. If the acceleration continues, then you would have the dominance of the strong coupling and in viability of the EFT. So we are just well ahead of, well before this epoch. Now, if this ghost field couples to the standard model through derivative vector coupling, the expression in the first line in blue, and symmetry psi equal psi going to just a phase times psi. So the fermions going transforming by this expression. And there is a mass term given by psi conjugate term. Then the vector coupling could not be removed. However, if phi and phi c are paired with a non-zero Dirac mass, the vector coupling could be removed, assuming that C psi and C psi conjugate is equal to 0. The axial coupling, however, could not be removed, and it leads to, so the first term leads to Lorentz and CPT violating term. So this mu psi bar gamma 0 gamma 5 psi leads to Lorentz and CPT violating term that gives rise to different dispersion relations for particles and antiparticles. So plus and negative signs are respectively for the left helicity particle and right helicity antiparticle. From the first term, you would obtain just a modified dispersion relation for particles and antiparticles. Also, if the Earth is moving with respect to the background, where the ghost field is isotropic, and if you assume that this isotropic background just coincides with the CMB background, this expression, the first expression would be proportional to mu times spin times velocity of Earth, and assuming that the velocity of Earth is about 10 to the power of minus 3 in natural units. So experimental bounds tell you that mu has to be less than 10 to the power of minus 25 GeV for electrons, and for protons and neutrons, mu has to be less than 10 to the power of minus 24. So the second term, this 1 over f mu s times, so s mu times di mu pi, leads to this kind of spin-dependent interaction, and exchange of pi would lead to a force which is constant in R but spin dependent. So the potential would take the shape of V, which comes at the bottom of the slide. So now let us try to couple a ghost condensate to gravity. The modification of the gravity becomes explicit in the unitary gauge. So one can break the time diffeomorphism by choosing the gauge in which the clock is given by phi. the Gauss condensate field. So in this case, time symmetry is broken, but the spatial transformations would be just unbroken, and we are interested in invariance under this residual spatial symmetries. So one of these invariants would be H00. So in order to restore full diffeomorphism by the Stuegelberg trick, so for that you have to assume that psi 0 is broken and is promoted to a field pi. So H00 would transform as the first expression, H0i, the expression in the middle, and Hij remains invariant under the Stuegelberg trick. So the kinetic term for pi would be produced by H00 square term. We also have this pre-knowledge that the extrinsic curvature is transforming like Kij plus Dij pi. So in order to have sixth order dispersion relation, we include the expression S in the unitary gauge action in addition to H00 squared. And we expect that addition of this term would introduce nabla cube pi square term. Now let us look at the modification of the gravity in the Gauss condensate in the Minkowski background. So you perturb the metric as ds squared just in the first line, adding the Newtonian potentials. And Einstein-Hilbert contribution enforces that in the Newtonian limit, omega squared is much less than k squared, omega squared is much less than k squared. The Newtonian potentials are equal to each other. The Lagrangian at the quadratic level would take the expression L effective. So you would obtain canonical field variables pi c and phi c by such expressions which have been provided. Also, we define the variable mu. And then the kinetic matrix of the Lagrangian takes expression which is in the white rectangle. And then if you just set the determinant of this matrix equal to 0, you would obtain omega squared proportional to k to power of 6 minus mu squared k to power of 4. And as you see, besides the sixth order dispersion relation, one would naturally obtain the quartic dispersion relation from mixing with gravity. And for k being less than mu, there is an instability. The width of instability in frequency gives the time scale Tc that a change in gravitational potential happens at the scales of mu to power of -1. So you can work out this instability frequency, and it's given by m to power of 4 divided by m Planck cube. So this would help us define just instability frequency upsilon, big upsilon. So in order to obtain the modified gravity potential, we need to compute the two-point function of the Newtonian potentials, which is given by the second expression in blue. And the correction to the Newtonian potential you can work out by having the omega minus k cubed being less than a term proportional to epsilon. So this time scale for instability is given by epsilon inverse. And this time scale, if you compare it for the case you have quartic dispersion relation, this time scale is m Planck over m larger than the corresponding time scale in the quartic dispersion relation. And due to the slowdown of the signal at RC less than TC. So basically, because our theory is Lorentz breaking, we have a slowdown of the signal. So you can look at the modification of gravity, and for that you decompose the Newtonian potential to two parts. One is given by phi n, and phi modified is the correction to the Newtonian potential. So you define kappa, big omega, script rho, and tau in the following fashion. And then you can work out just the modified potential, potential. And you see that initially for small time variables, the oscillations are fast until you approach tau equals to 1, and then the amplitude of the oscillations in the potential becomes just smaller, but their frequency becomes small. Their period becomes larger, but after tau equals to 1, then the amplitude starts to increase again. And what happens is that the amplitude of oscillations would also, the frequency of oscillations would also decrease. So now let us look at the Gauss condensate coupled to gravity in de Sitter or general FRW background. So you have Einstein-Hilbert term and the Gauss condensate term, and you look at the perturbed metric, which is now the spatial part has the scale factor square term, and we expand the Gauss condensate term in terms of phi and psi, and we recover the Goldstone boson pi using the Schick-Elberg tree, and then we would obtain the Gauss condensate action at the bottom of the slide. Then we vary the action with respect to G mu nu, and we would obtain the equation labeled by a star. And kappa rho lambda are complicated expressions of the extrinsic curvature and its derivative, and G rho lambda is the Einstein tensor. If the coefficient of the sigma 1 operator is equal to 0, then one can show that the off-diagonal components of the equation labeled by a star would be equal to each other. And then varying the action with respect to pi and using the equations, the three equations in equation star, one can obtain the equations of motion for dark energy. So you would obtain the expression at the bottom of the page. And the newcomer variables are given by these expressions, S2, S3, S4, and C1 to C8. And you can see that the speed of sound of dark energy perturbations is given by C7 over C4. And in general, it is different than 1. So now you can also just solve the equation of motion for the Newtonian potential. and you would obtain the first equation at the top of the slide. For distances bigger than h minus 1, phi is given by two damping exponentials. If you decompose phi in terms of to phi gr and phi which is coming from ghost condensate, where phi gr is satisfying the Laplace equation given by the expression at the bottom of the slide. And if you assume that SIs are of the same order and they are defined by these expressions, and alpha beta are defined as such, and X is given by mu R, then the Gauss condensate contribution to the potential satisfies this equation at the bottom of the slide. And here we have also assumed that we have time-independent solution. So we have neglected the time derivative of the potentials. So one can see that the Gauss condensate potential is dependent on the spatial derivatives of rho, the matter density, in addition to rho itself. For the quartic dispersion relation, only the density of the matter becomes important, not the spatial variations of rho. But for sixth order dispersion relation, you would obtain the variations of also rho as well. So you can set the matter density equals to 0, and for different choices of the initial conditions. So for example, if you set the just the field itself to be negligible, but the second derivative and the fourth derivative equal to 0, you would obtain the graph, the graph in blue, the line in blue. And if you assume, for example, only the second derivative is non-zero, you would obtain the line in red, and the line in purple is the one in which the fourth derivative of the field is set to be non-zero. And if you assume that there is a matter profile, like what I have given, just rho over ms squared given by this expression, so basically just goes to 0 at large values of x, then you would obtain the potential times x, of course. I have to emphasize that basically what we obtain is phi times x. So basically phi is proportional to 1 over x. You would see that the GR component is just the one which is given by the green line, and the orange line is the contribution of the Gauss condensate, and alpha and beta are given by these values at the right of the graphs. One interesting thing is that if you look at the tensor perturbations contribution to the metric, so if you look at the hij, script hij, where hii is equal, so basically it's traceless and it's also transverse, so di hij is equal to 0. You would see that the term proportional to S1, so which was this term, adds this contribution to the action for tensor perturbations. And from that, one would obtain a modified speed of gravitational waves given by this expression. So you see that it's momentum dependent, and deviation from the speed of sound equals to 1 becomes important around the momentum close to m Planck. Sorry, this should be m Planck over a square root of sigma 1. So, and one one observes a substantial modification to the speed of gravitational wave is if k is m Planck over square root of sigma 1. And in order for gravitational waves to be subluminal, sigma 1 should be equal or less than 0. K has to be between H and M, where the latter inequality comes from the viability of the effective field theory. And in order to see substantial deviation from the luminal propagation of gravitational waves, if you assume that K is of order of M, which has to be of order 10 to the power of minus 3 electron volt, if it's supposed to be explaining our dark energy value, then sigma 1 has to be of order of 10 to the power of 60 in order to see substantial deviation. But for K's of order, the Hubble parameter, sigma 1 has to be larger, 10 to the power of 120. So from the LIGO-Virgo observation of the binary neutron stars, CT minus 1 has to be between 7 times 10 to the power of minus 16 and minus 3 times 10 to the power of minus 15 in the frequency range f between 10 hertz and 10 kilohertz. So if you impose this constraint on the speed of gravitational waves, you see that if you assume that the frequency is 10 hertz, sigma 1 has to be less than or equal 10 to the power of 69, and for 10 kilohertz, sigma 1 has to be less than 10 to the power of 63. So let me conclude my talk. Gauss condensate is an IR modification of gravity with no strong coupling in the UV, in which the additional degree of freedom acquires a non-standard dispersion relation. We exercise the Sextic dispersion relation, noting that the accelerated expansion of the universe is a recent cosmological phenomenon. If the Gauss condensate field is coupled to a standard model, the axial coupling gives rise to different dispersion relations for particles and antiparticles. Also, it produces a spin-dependent, scale-independent force from the exchange of the Gauss condensate perturbations. The instability at the scales of mu inverse occurs at time scales of m Planck over m Planck cube over m to the power of 4, which is which is m Planck over m larger than the quartic dispersion relation. The potential phi, Newtonian potential, acquires oscillatory features in the scales of mu inverse over the time scale Tc. For the Gauss condensate with a 6th order dispersion relation and in an expanding background, the equation of motion for Gauss condensate phi is governed by the spacetime variations of ρ2. Again, the potential acquires oscillatory features on top of 1 over x behavior. The term in the unitary gauge action induces correction to the gravitational perturbations and modify the speed of gravitational waves as such. And thank you very much for your attention.
Thank you. Very nice talk. Any question? Seems there is no question. Thank you again. So we can close the first day. and we'll begin tomorrow with poster presentation. Thank you, Amjad.
No problem. Thank you very much for giving me the opportunity to speak.
Thank you, and if there is no comments or question, goodbye today. See you tomorrow.
Goodbye.